Um, so I'm gonna get started. Just a second. I need to do something real quick. Um, so I'm gonna get started with announcements. So we're having class remotely because of the weather, because campus is closed. Because of this, there will not be a lab because lab requires us to be physically in the lab. We'll just push everything back. We'll catch up. I'll adjust. Um, so homework wise, uh, chapter 1.1 homework is due tonight, Monday the 26th. Chapter 1.2 is due Wednesday the 28th. Chapter 1 quiz will be in lecture on Wednesday the 28th. The significant workers worksheet is also due Wednesday the 28th in class. Uh, the first chapter 2 homework is due next week, Wednesday, the 4th, and the second one is due on the 11th. And if you have any past due assignments, you can request an extension. The best way to do that is to go to the assignment and choose automatic extension. Um,
Professor, I have a question.
yes,
Will you by any chance be having a study guide for the quiz, or is it just sit there and do
it's
it?
just the material from the lecture. I mean,
Oh, all
you
right.
can, there are on Blackboard, there are like review packets that you can look at, but otherwise, there's not like a specific targeted study guide. You can always look at the slides and such. Um, so on Blackboard in the uh, whatchamacallit, what did I call the section? Let me look at it. General science. There's the review material, and that has unit reviews with and without solutions and chapter recaps that you can look over. Um, but there's not like a specific study guide. It's just the material from the lecture. So continuing on from where um, we were talking about speed and velocity. So average speed is a measure of, the average rate that how fast you're traveling. An average speed, it's what you'd normally think of as the average speed, the distance traveled over the time it took to travel that distance. Um, so average speed is distance over time, or change in distance over change in time is a way you can think about it. And the distance is the actual path length traveled. So the average speed depends on the actual path length traveled, because again, speed is a scalar. And the instantaneous speed is the speed of an object for an instant of time, where delta t, the time period you think about, is very small. That's what you get if you glanced at a speedometer. So a speedometer is something that's sort of actively measuring your instantaneous speed. Um, Velocity is similar to speed, except there's a direction involved. And because there is a direction involved, um, it is possible to have an average velocity where your speed is always some value, but because you go in different directions, uh, your velocities can cancel out because of the direction. So the average velocity is your displacement, which is your final position minus your initial position. It's the straight line distance between the initial and final position with a direction towards the final position. Um, and so the average velocity is your total displacement over your total travel time, which means it's possible your um, average speed will depend on the path you take, while your average velocity will not. So it's possible to have an average speed that's a very large value, but an average velocity that's, say, zero because you ended where you started. So your displacement was zero. And instantaneous velocity is similar to instantaneous speed, except it has a direction. Uh, the idea being that for average velocity, you're combining all of these things that have a direction, and the directions can sort of cancel each other out. So here is sort of a difference between displacement and distance. Distance depends on the path taken. So if I go up and around this upper path, let me kind of up and around this upper path here, it'll be a different distance than if I take this lower path, which is probably shorter. But they have the same displacement because they both start at the same place and end at the same place. So displacement's a vector quantity between 2 points. It does not depend on the path. Distance is the actual path taken. So here we have an example where we can see the difference between distance and displacement, and an example of adding vectors. So here we have a person traveling along. They go 2 meters uh, to the right, 1 meter down, another 2 meters to the right, and then another 2 meters down. To figure out the distance, you'll add up each of these individual distances. So 2 meters plus 1 meter plus 2 meters plus 2 meters. That adds up to a total of 7 meters. Um, okay, something. Um, as you can see here. Uh, but to find the displacement, you need to find the straight line distance from the start to the end, which you can do with the Pythagorean theorem. Um, from here to here is 4 meters, and from here to here is 3 meters. So this distance, because this is a right triangle, can be found using the Pythagorean theorem. This length c is going to be the square root of 4 squared plus 3 squared, because c squared equals a squared plus b squared. So the displacement is 4 meters squared plus 3 meters squared, which is 16 plus 9, which is 25, and the square root of that is 5. So this distance c is 5 meters. And the direction is southeast. And then let me clear those drawings and proceed to the next slide. So that's how you can handle adding vectors. The general way that you add vectors, well, is you connect vectors head to tail. So if I have some vector A and some vector B, I can connect vector B starting its tail at the head of A, and just sort of it's the whole sequence of movements. So this, I go along A and then I go along B. That direct connection from the start of A to the end of B is A plus B. Additionally, and what you can also subdivide vectors along the axes. You have the direction along the x direction and the direction along the y direction. And the total vector is the x direction the vector in the x direction plus the vector in the y direction. So you'll get the total vector squared is ax squared plus ay squared. Um, I think you only have like one problem on your homework you'll need to do this, and I won't be putting it on the quizzes, but this sort of just wanted to express how vectors work. Now, if you're moving at constant velocity, you'll have a really your average velocity is displacement over time. So here we have a car moving at constant velocity, uh, and we want to describe the speed of this car. Well, the average speed is distance over time. This car moves 20 meters every second in the same direction. Um, so every second, this car moves 20 meters. So over a total of 4 seconds, it will have moved a distance of 80 meters. So our total distance is 80 meters and our time is 4 seconds. So speed will be distance over time. So that's 80 meters over 4 seconds. That's 20 meters per second is our average speed. Our velocity in this case would be uh, 20 meters per second in whatever the direction of motion is. So in this case, you could say that maybe it was uh, perhaps this direction is the plus x direction. So it's 20 meters per second in the positive x direction, or it's 20 meters per second to the east. Because most of the problems we're going to be dealing with will be one-dimensional. Often you can just say this would be maybe positive 20 meters per second. Now, if you want to figure out how far the above car would travel in 10 seconds, well, velocity is distance over time. If we multiply both sides with time, we get velocity times time equals distance. So our or in this case, actually, it's speed times time equals distance. Sorry. In this case, but velocity times time equals displacement if velocity is constant. So 20 meters per second times 10 seconds gives us 200 meters. If something is traveling at 20 meters per second for 10 seconds, it will have traveled 200 meters. And you might want to work out what's going on, and just make sure you've got your units set up appropriately. But that's sort of the question here. So let's do a problem about something with speed and distance. How long does it take sunlight to reach the Earth from the sun? Well, we know how fast light travels. The speed of light is 3 times 10 to the 8th meters per second. The distance to the Earth is 1.5 times 10 to the 8th kilometers. Well, the first step we have to do, since we have a speed in meters per second and a distance in kilometers, let's get everything in the same units. So first we're going to convert the distance to the Earth from kilometers to meters. And to do that, we need to multiply by 1,000, or 10 to the third. So 1.5 times 10 to the 8 kilometers is 1.5 times 10 to the 11 meters. Now we want to find time. So if we solve speed equals distance over time and rearrange to solve for time, time equals distance over speed. So time equals distance over speed. That's 1.5 times 10 to the 11 meters divided by 3 times 10 to the 8th meters per second. 1.5 divided by 3 is 0.5. 10 to the 11 divided by 10 to the 8. 11 minus 8 is 3. So that's 10 to the third. So we have 0.5 times 10 to the third seconds. But we'd like this in standard scientific notation. So we will multiply. We will move the decimal place 1 point to the right and subtract 1 from the power of 10. So that's 5.00 times 10 to the 2 seconds, or 500 seconds. So it takes 500 seconds, or about 8 1/3 minutes, for light from the sun to reach the Earth. Another question we can ask is, what's the average speed in miles per hour of the Earth revolving around the sun? Well, first, we know the time. The Earth revolves around the sun once every year. That's 365 days. We need to convert that to hours. And we know the Earth's radius, which is 9.3 times 10 to the 7 miles, 93 million miles. But we need to find the distance the Earth travels in 1 year revolving around the sun. And that's the circumference of a circle of radius 93 million miles. So first, we have to convert 365 days to hours. 365 days times 24 hours per day is 8,760 hours. Then we need to find the distance. A circle's circumference is 2 pi times the radius. We know pi, we know the radius. Therefore, the distance is going to be 2 times pi, 3.14, times 9.30 times 10 to the 7 miles. Because we have a circle of radius 93 million miles. So if we want to solve the equation, our average speed is the distance over time. So 2 times 3.14 times 9.3 times 10 to the 7 miles divided by 8,760 hours gives you 0.00667 times 10 to the 7 miles per hour. And we'll need to adjust the decimal point. We'll just move it 1 to 3 places to the right, which will decrease the power by 3. So 6.67 times 10 to the 4 miles per hour, or 6,600 or 66,700 miles per hour. We can also ask a similar question about how fast we're traveling around as the Earth spins. And let's do that at the Earth's equator because it's the easiest place to do it. So the radius of the Earth is 4,000 miles. The time it takes for the Earth to rotate once is 24 hours. So the circumference of the Earth is 2 pi times the radius. That's 25,120 miles. So if we divide that by the time, we can find the speed. So 25,120 miles divided by 24 hours gives us 1,047 miles per hour. And sort of an idea is, speed is going to be distance over time. So miles per hour. So we have a distance in miles divided by a time in hours. That's sort of a general way you can approach these sort of problems, where you sort of look at the units you're supposed to have in your answer and look at the units of what you have in your givens, and you can sort of guess what the formula is going to be. So here, this is a question about finding speed, but it does involve a little bit of unit conversion. So there's two ways you can approach the unit conversion for this problem. So the question is, a car travels 300 kilometers due north in 3.5 hours. And the question is what's the car's velocity in meters per second? So there's two ways you can approach this. You can either first convert the distance to meters and the time to seconds and then do the calculations. Or the other way is you could do the calculations, find the speed in kilometers per hour, and then convert kilometers per hour to uh, meters per second using the conversion for that 1 meter per second is 3.6 kilometers per hour. So, additionally, the other useful conversions here that I haven't written on the slides yet. Um, just 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds. So I'll give you a couple minutes to think about this problem. I'm going to fix these errors real quick. This is 1,000. This is 3,600. Okay. So 300 kilometers is 300,000 meters. 3.5 hours times 3,600 seconds per hour is 12,600 seconds. So velocity is displacement, 300,000 meters north, divided by 12,600 seconds, gives us 23.8 meters per second north. The other way you can solve this problem is 300 kilometers divided by 3.5 hours gives you 85.7 kilometers per hour. And then you multiply by 1 meter per second is 3.6 kilometers per hour. And that gives you also 23.8 meters per second north. Did that make sense? Any questions? Okay.
I have a question. Where do you get a 30,000 or 300,000 for the displacement?
So 300 kilometers times 1,000 meters per kilometer to get 300,000 meters.
Okay, I see. Thank you.
Um, so here is a very similar question. If a car travels 300 kilometers due north in 3.5 hours, what's the car's speed in meters per second? Well, you would do this problem pretty much the same way, except you don't take into account direction. 300 kilometers is times 1,000 meters per kilometer gives you 300,000 meters. 3.5 hours times 3,600 seconds per hour gives you 1,200, sorry, 12,600 seconds. Um, mm. So speed is distance over time. That's 300,000 meters divided by 12,600 seconds. That is also 23.8 meters per second, but there's no direction involved here. Since this car is traveling in a straight line, uh, its average velocity, the size of its average velocity will just be its average speed. So here we have a bullet traveling at 335 meters per second for 2.5 seconds. How far does it travel? Remember that, you know, speed or velocity equals displacement, velocity equals displacement over time, or speed equals distance over time. You can use either equation for this. They're functionally the same because it's a straight line. So this is the relevant equation. I'll give you a minute or so to work on this. Okay. So we want to find the distance or the displacement. So for constant velocity, displacement is velocity times time, or distance equals speed times time. So the distance here is going to be 335 meters per second times 2.5 seconds equals 837.5 meters. But both of our starting values only have three significant figures, so you would round that to 838 meters. Um, and I will continue. So we were talking about speed and velocity. Um, Trying to get us to the right place. So we talked about speed and velocity. Speed is distance traveled over the time it took to travel that distance. Velocity is displacement over travel time. It's the rate of change of position. But velocity is not always constant. You're not always moving at the same speed. You're not always moving in the same direction. So sometimes we want to talk about how velocity changes. And for that, we talk about acceleration. So changes in velocity can occur in three ways. You can either increase the magnitude of your velocity, you can speed up, you can decrease the magnitude of your velocity, you can slow down. For the first part of this, so speeding up, slowing down, it's very straight line motion. That's straight line motion. And then lastly, you can change the direction of your velocity vector. You can turn. And when any of these changes occur, the object is accelerating. However, um, in general, we can, what's going on? Sort of split this into two groups. This is, the straight line changes. And then this is circular motion. So this is, circular motion, uh, which I change in direction is circular motion, and increasing magnitude or decrease in magnitude, that's straight line motion. So for the first part of the chapter, we're going to talk about just straight line motion. And then later we'll talk about circular motion separately. And we're not going to talk about them combined because that's complicated enough to be beyond this class. But when any of these changes occur, uh, the object is accelerating. And the faster the change, the greater the acceleration. And you feel acceleration. If you've ever been in a car that's speeding up, you can feel yourself pulled in the opposite direction. That's because your body is catching up and you feel that force pushing you. We'll talk about the relationship between force and acceleration in chapter 3, but acceleration is something you can feel. Similarly, if you slow down, you feel pulled forwards, and you feel pulled to the opposite side when you turn. You feel acceleration. So an acceleration is the measure of the change in velocity during a given time period. So it's change in velocity over the time for that change to occur. So it's final velocity minus initial velocity over time. And because it's change in velocity over time, let me turn on the laser pointer again. Because it's change in velocity over time, the units are velocity, meters per second, over time, seconds. So meters per second divided by seconds gives you meters per second squared. So acceleration will have units of meters per second squared. Acceleration, we're going to limit ourselves to the more basic case in this course of situations with constant acceleration. Reality is not so pretty, but situations with constant acceleration are actually pretty common. So we will limit ourselves to constant acceleration, and it'll be good enough for this class. But there are, in fact, terms for the rate of change of acceleration. The rate of change of, acceleration is the rate of change of velocity. The rate of change of acceleration is called jerk. And it turns out you can keep going. The rate of change of jerk is either called snap or jounce. And if you call it snap, the rate of change of snap is called crackle, and the rate of change of crackle is called pop because someone thought they were funny. But the general thing is that we're only going to deal with constant acceleration. You don't need to know any of those other terms. No one really uses anything beyond jerk as a name. You can express it in other ways that is perfectly clear. But general idea is that acceleration is change in velocity over change in time, which is final velocity minus initial velocity over time. Uh, because it's velocity over time, it's meters per second or meters per second squared. Um, and then we can take this equation. If we have constant acceleration, we can work from that and figure out some formulas for how velocity changes over time given a constant acceleration, and then actually how position changes over time given a constant acceleration. So if you have an object undergoing constant acceleration, one of the most common forms of constant acceleration is a falling object. If you drop something, it will accelerate downwards at a constant 9.8 meters per second squared. That is the acceleration due to gravity. And as the velocity increases, as it falls, as time goes on, the object will speed up. So the distance it travels every second will increase. Uh, so the distance between each second of time will get bigger and bigger. So if you drop an object at time t equals 0 and velocity equals 0, the total distance traveled will be 0. After 1 second, your velocity will be 9.8 meters per second, and your total distance traveled will be 4.9 meters. After 2 seconds, your velocity will be 19.6 meters per second, and the total distance traveled will be 19.6 meters. After 3 seconds, your velocity will be 29.4 meters per second, and the total distance traveled will be 44.1 meters. And after 4 seconds, your velocity will be 39.2 meters per second, and the total distance traveled will be 78.4 meters. So if we want to find the acceleration of something, uh, like a race car starting from rest, if we have a race car that starts from rest and it accelerates uniformly along a straight track and it reaches a speed of 90 kilometers per hour in a time of 7 seconds, and we want to find its acceleration. Um, so because this race car started from rest, we know our initial velocity is 0. Um, we know our final velocity is 90 kilometers per hour. And we know our time is 7 seconds. Well, the first thing we need to do is we need to convert our final velocity from kilometers per hour to meters per second to find acceleration in meters per second. We want our acceleration in meters per second squared. So we need to convert 90 kilometers per hour to meters per second. 1 meter per second. Let me stop this. 1 meter per second is 3.6 kilometers per hour. So 90 kilometers per hour divided by 3.6 kilometers per hour times divided by 1 meter per second over 3.6 kilometers per hour or times 0.278 meters per second over 1 kilometer per hour gives us 25 meters per second. 90 kilometers per hour is 25 meters per second. Then our acceleration is going to be our final velocity minus our initial velocity over time. So that's 25 meters per second minus 0, because we started at rest, over 7 seconds. So 25 divided by 7 gives us, rounded to two significant figures, 3.6 meters per second squared. That's our acceleration. Now, this form of the equation is not always the most useful version of this equation. Let me clear the. So we know acceleration is final velocity minus initial velocity over time. However, a lot of the time we know the acceleration and we want to find we know the starting conditions. We know the acceleration, we know the initial velocity, and we probably know the time. And we want to find how fast we're going after some amount, of time. So we know the starting conditions, the acceleration, and the initial velocity, and we want to find out our velocity after some time. So we can rearrange this equation. If we multiply both sides by time, we get acceleration times time equals final velocity minus initial velocity. And then we can add initial velocity to both sides and get final velocity equals initial velocity plus acceleration times time. And this equation is very useful for finding final velocity. And I also have the equations for finding initial velocity, which is final velocity minus acceleration times time, and time, which is final velocity minus initial velocity over acceleration. So if you're looking for any of those three, that's how you can find them. These are all the same equation, just rearranged. But this version is very commonly used because it's useful for finding final velocity given initial conditions. So we have the car for the previous example, which has an acceleration of 3.57 meters per second squared. Um, and we want to find the magnitude of its velocity at the end of 10 seconds. Because if the car in the preceding example continues to accelerate at the same rate for 3 more seconds, so a total time of 10 seconds, what will be the magnitude of its velocity in meters per second at the end of this time? So our acceleration is 3.57 meters per second squared. That's 25 meters per second divided by 7. Our total time is 10 seconds. Our initial velocity is 0. We started from rest. So our final velocity is our initial velocity, 0, plus 3.57 meters per second squared. Our acceleration times time, 10 seconds, which gives us a total distance of 35.7 meters per second. It's also possible to solve this uh, by instead using the end of the previous problem as your starting velocity. So you have, V naught would be 25 meters per second. Acceleration would be 3.57 meters per second. And time would be 3 seconds. And that will give you the same final velocity. But in this particular case, the numbers are nicer uh, if you just start from your original 0. So, since velocity is a vector quantity, it has a magnitude and a direction. Acceleration is one as well. So there's sort of when we're talking about things, we might talk about acceleration and deceleration, meaning speeding up and slowing down. Acceleration or speeding up is going to be when your acceleration and your velocity are pointed in the same direction. That's going to speed you up. Deceleration, slowing down, occurs when your acceleration and your velocity point in opposite directions. That's when you're going to slow down. Um, so if velocity is positive, well, positive acceleration will speed you up and a negative acceleration will slow you down. If velocity is negative, A positive acceleration will slow you down, and a negative acceleration will speed you up. But again, the acceleration is also a vector. So here's another question about average acceleration. Um, and I'll give you a couple of minutes to solve this. So a car goes from 0 to 108 kilometers per hour in 10 seconds. What is the car's average acceleration in meters per second squared? And a helpful conversion factor is that 1 meter per second equals 3.6 kilometers per hour. So to go from kilometers per hour to meters per second, you divide by 3.6. And remember, acceleration is change in velocity over time. So let me write that on here because normally I would have it on the board. Yeah, acceleration equals v final minus v initial over time. So I'll give you a couple of minutes to solve this. Be back. Oh. So first we need to convert our final velocity from 108 kilometers per hour to meters per second. So 108 kilometers per hour times 1 meter per second over 3.6 kilometers per hour gives you 30 meters per second. Acceleration is final velocity minus initial velocity over time. So we know our final velocity, it's 30 meters per second. Our initial velocity is 0, and our time is 10 seconds. So 30 meters per second minus 0 meters per second over 10 seconds gives us 3 meters per second squared. That will be the acceleration of this car. Here we have another acceleration problem, but here instead of speeding up, we're slowing down. Here we have a car traveling at 120 kilometers per hour, and it slams on its brakes and comes to a stop in 1.2 seconds. So what's the average acceleration of this car? Remember acceleration is final velocity minus initial velocity over time, and 1 meter per second equals 3.6 kilometers per hour. So I will again give you a couple of minutes to solve this. Okay. So here, the main difference from the previous problem is that we are given a initial velocity and our final velocity is zero. Um, so first, let's figure out our initial velocity, 120 kilometers per hour, times 1 meter per second divided by 3.6 kilometers per hour is 33.3 repeating meters per second. I'm not going to round until the end. Our acceleration is our final velocity minus our initial velocity over time. So here, 0 meters per second minus 33.3 repeating meters per second over 1.2 seconds gives us an acceleration of negative 27.7 repeating meters per second squared, or negative 27.8 meters per second squared. And it's important that you list the acceleration as negative because the sign is important to indicate the direction. And here we have a problem of finding the final velocity. So instead, instead of the version of this equation we have here, um, we can use final velocity is initial velocity plus acceleration times time. Um, so here we're finding the final velocity. Um, we know our initial velocity. We know our acceleration. We know our time. Oops. Oh, so let me clear all this. I did put these in. So here's how you'll approach that. Uh, acceleration is final velocity minus initial velocity over time. If we rearrange that, we get final velocity as initial velocity plus acceleration times time. So final velocity is the initial velocity, 1 meter per second, plus 4.5 meters per second squared times 2 seconds, which gives us 1 meter per second plus 9 meters per second, or 10 meters per second. So our final velocity in this case is 10 meters per second. Now, as previously mentioned, there is a special case. Falling objects, the acceleration due to gravity on Earth is at a constant altitude is constant. Um, so that means any object you drop will fall at the same acceleration, discounting air resistance. So the direction of the acceleration is down towards the center of the Earth. And that acceleration is denoted by lowercase g, and that acceleration is 9.8 meters per second squared. Technically, it varies depending on where you are, but we will be using 9.80 meters per second squared in this class. So every second, a dropped object will speed up by 9.8 meters per second. So this is the velocity of a dropped object as a function of time, and the distance it's traveled would be a parabola. This increase in velocity is linear. Now, unfortunately, we live in the real world where there is air that slows dropped objects down. So if you can neglect air resistance, every freely falling object will fall on the same rate regardless of the mass. And the person who originally discovered this and worked it out was Galileo. Um, and if you take a tube and pump all the air out and drop a feather and a penny, the two objects will fall at the same rate and will land at the same time. Um, this was most dramatically demonstrated by astronaut David Scott on the moon, where he simultaneously dropped a feather and a hammer. Um, and each fell at the same acceleration due to there being no atmosphere and no air resistance. And because it was on the moon where gravity is weaker and that acceleration is slower, it was easier to see. And this is what it looked like. Uh, what is going on? Uh, that was not what was supposed to happen. Okay, first of all, let's just turn off the laser pointer. Second, yes, let me. There we go. Close this. And here is that video of that dropping.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
There.
Which proves that Mr. Galileo was correct in his findings.
They fell quite clearly at the same rate. And Galileo is credited with using the Leaning Tower of Pisa as an experiment site to drop objects to see them falling at the same rate. I think that's where we're going to stop for today. Just a quick reminder. So there's no lab today, but we will have the quiz on Wednesday in lecture. We'll have lecture for the first half of class and the quiz for the second half. Any questions before I let you guys go? Okay, have a nice day. I'll see you all on Wednesday. Hopefully the weather will be better.
Have a good one.
Mm-hmm. And